All right, so these notes are on surfaces in space. We just spent a lot of time talking about lines in space and planes in space, and now we're going to talk about surfaces in space. And we're going to talk about two different types. There's cylinders, and then there's surfaces of revolution. There are other surfaces in space, but this is where we're going to start. So, a cylinder in calculus isn't what you're used to thinking of a cylinder. A cylinder in calculus is when you take C, a curve in a plane, and let L be a line not in the parallel plane. The set of all lines parallel to L and intersecting C is called a cylinder. C is called, pardon me, the generating curve, or the directrix of the cylinder, and the parallel lines are called the rulings. Now, I'm terrible at drawing these freehand, so we're going to do our best here. So if I look at this, basically what you need to know is the equation of a cylinder is going to have two variables. The cylinder then runs along the axis of the missing variable. So this thing right here, believe it or not, is a cylinder in space. What we have is this generating curve C that's on the XZ plane, this curvy thing right here. That's your generating curve. And then basically we just stretch it out and repeat it over and over and over again into the Y direction, and that's what gets you your cylinder. So a cylinder is really just like a sheet of twisty piece of paper, if you want to think of it that way. Now, what variable would be missing from this equation? Well, the missing variable is the axis it runs along, so this equation would be missing the Y variable. And what would a possible equation be? Well, this kind of looks like a cube root function, but maybe shifted a little bit. So let's say that's where the center is. So this could maybe be like z equals the cube root of x plus 1 maybe, because I've shifted left 1 and up 1 along the z-axis. Now that's just a possibility. I don't know. Ooh, and actually, let's see. If we consider this, I'm going to consider this one the positive x-axis and not the negative. So there's a possibility. I'm not ever going to ask you to figure that out, but I just wanted to give you an idea of this could be the equation of the cylinder. All right, so down here we're going to sketch a couple cylinders. So let's say I want to sketch y equals x squared. Basically, all you do is you start with your x, y, z axes, these guys right here, and then you draw the generating curve. So y equals x squared would really be like a parabola. So I could say, well, this thing right here is y equals x squared drawn on the xy plane. Then if I want to actually make it a cylinder, what I do is just basically stretch these up and kind of connect them with another parabola here. This should touch the z-axis. There we go. That's a little bit better. So this is what our cylinder would look like, and it would kind of be, you know, coming around here like this, and then it goes back there like that, and you really just have a curved sheet of paper in the shape of a parabola. X squared plus y squared equals 9. Well, that's a circle. So if I take x squared plus y squared equals 9, it kind of looks like this, and then I just pull it along the z-axis, and I have more what looks like a typical cylinder. And then z plus y equals 3, I would graph on here. Here's z, here's y, here's x. Z plus y equals 3, I'm going to think of this as z equals 3 minus y, because it makes it easier to draw. So 3 minus y would look like this. And then this shifts along the x-axis. So this is really a tilted plane. Those are technically all cylinders. Okay? Now, on to surfaces of revolution. So if you remember from BC Calc, you had stuff where you had like y equals the square root of x, and then you spin it around the x-axis, and you had to find the volume of the solid. You remember those? Well, technically, this outside part here is what's called a surface of revolution, and we can make its equation in 3D. So, if the graph of a radius function r is revolved about one of the coordinate axes, the equation of the resulting surface of revolution has one of the following forms. If you revolve it around the x-axis, The form of the equation is y squared plus z squared equals r of x squared. In other words, this is going to be expression in terms of x. Then if you revolve around the y-axis, y is missing from the squareds, but you're in terms of y over here. Along the z-axis, z is what you're in terms of, and z is missing from the sum on the other side. This makes a lot more sense when we do it. So, write an equation for the surface of revolution by rotating y equals x about. So, y equals x looks like this. And then if I spin it around the x-axis, it looks like that. I have two cones. So if I spin y equals x around the x-axis and I want to write an equation for it, as soon as I see x-axis, I know I have to start with y squared plus z squared. Then this r of x component means take your equation of revolution and get it in terms of x. Well, it's already in terms of x. It's in y equals form. This is in terms of x. So I get x squared. The equation of this cone, this pair of cones, would be y squared plus z squared equals x squared. Now let's say instead of revolving around the x-axis that I instead revolved around the y-axis. So here's y equals x here. I spin around the y-axis. I get these vertical cones. That equation would be x squared plus z squared equals y squared. All right, z equals 4y squared. So I'm going to sketch it here. So here's z, here's y, here's x. Z equals 4y squared would look something like this, a little bit narrower, but you get the idea. It's a parabola. And if we spin that around the y-axis, we get something that kind of looks like a double-sided trumpet here. So if I spin that around the y-axis and I want the equation, I just start with x squared and z squared. And then I have to get my equation in terms of y. It is currently in terms of y. It's 4y squared. So I take that and then I just square it. So the equation would be x squared plus z squared equals 16y to the fourth. Now if instead I spin around the z-axis and I get like a bowl thing, whoop, it's going to kind of look like this. If I spin it around the z-axis, I'm going to have x squared plus y squared to begin with. Then I need to take this and put it in terms of z. So I need to solve for y. So if z equals 4y squared, then y squared equals z over 4. And y equals plus or minus the square root of z over 4. Now, if I spin that around the z-axis, I don't really care about the plus or minus so much. So I'm really just going to have the square root of z over 4 squared, which is going to give me x squared plus y squared equals z over 4. All right, and then last but not least down here, we have, what is going on? Sorry, having computer difficulties here. Last but not least here, we have find a potential plane equation that creates the equation x squared plus y squared equals 9z squared. What is the axis of revolution? Well, this is the easier one to answer. The axis of revolution is going to be the z-axis because z is missing on this side and exists on that side. Now, find the equation. Well, remember, 9z squared is r of z squared. So if I square root both sides, my r of z is going to be plus or minus 3z. Now that means that I have an equation that in terms of z is written as y as plus or minus 3z. So there are two options. It could have been the equation x equals plus or minus 3z, and it also could have been y equals plus or minus 3z, but we're just not sure which. So that's why it says find a potential plane equation. It's in either an x equals or a y equals, and I don't know if it was positive 3z or negative 3z in that case. Okie doke. All right, then find a generating curve in the axis of revolution for the surface given by that. So I need to make this look a little bit more like the other equation. So x squared plus z squared equals 9 minus 3y squared. So then my generating curve would be x or z equals the square root of 9 minus 3y squared. Okay? Again, axis of revolution is whatever's missing over here. I'm missing the y, so our axis of revolution is the y-axis. And my generating curve is just the square root of the right-hand side. Alrighty. Now, this, it says use your book to review the quadratic surfaces, look at the standard forms of the surfaces, notice what's unique about it. Obviously, you don't have your book in front of you, but if you could get your book in front of you, it would show you some setups. So I'm going to take a second here, and I am going to bring up the book image onto this page so I can refer to it. All right, so this is in your book toward the last pages of this section. And if you can get your book out and have it next to you, then you don't have to keep scrolling back and forth with me. But at the end of this section, they give you a listing of what are called the quadratic surfaces, some of which are surfaces of revolution, some are not, but that's okay. And all of these surfaces are listed for you in your book on page is, now I can't find it myself here, where are they? There they are, on page 812 and 813 in your book. But I have a condensed version right here. But basically, this grouping here gives you a bunch of quadratic surfaces. There's something called an ellipsoid, where x, y, and z are all on the same side of the equation. They're all squared, they're all positive, and they're set equal to a positive number. An elliptic paraboloid are where x and y are both squared and positive, but they're set equal to a z that is not squared. A hyperbolic paraboloid, also known as a saddle, is again x squared and y squared set equal to z that's not squared, but instead of adding them, you're subtracting them. A cone, x, y, and z are all squared, but z is on the other side and there is no remaining constant. A hyperboloid of one sheet, x, y, and z are all squared, and if you get them on the same side, one of them is negative, and it's set equal to a positive number. Hyperboloid of two sheets, same idea, but two things are negative. Now, what I want you to really understand with this is how to identify what's missing and what's available to you to use. So if we come up here, and I said, well, let's use that chart to identify the surface type and the axis of rotation, x squared, y squared, z squared, they're all squared, they're all positive, and they're set equal to a positive number, this would be an ellipsoid. And there is no axis of revolution because technically you could revolve it around any of the axes if any of them are circular. So we're just going to ignore that for this one. What about 9x squared plus 4y squared plus z squared equals 3? Again, this is another ellipsoid. But again, we do not have an axis of revolution for this one. X squared plus 4y squared plus 9z equals 0. All right, well, this is different because it's not set equal to a positive number. It's set equal to 0 this time. And this, when it's set equal to 0, is really just going to be a point. Because what set of three numbers can I square, multiply, add together, and get 0? Well, unless I deal with complex numbers, the only way I can do that is with zeros to begin with. So this is really just a point. It's the origin. X squared plus 4y squared plus 9z squared plus 10 equals 0. Well, if I move this 10 over, now I have an ellipsoid with a negative radius. No, this is an impossible kind of thing, at least in the real number system. Complex analysis, that's something different. X squared minus y squared plus z squared equals 1. Okay, so I've got three squareds, one's negative, and it's set equal to a positive number. Let's see, 3 squareds, 1 is negative, and it's set equal to a positive number. Here we go. That's going to be a hyperboloid of one sheet. So this is a hyperboloid of one sheet. And with that hyperboloid of one sheet, the unique variable would be the y variable because that's the only one that's negative. So the y-axis would be your axis of rotation for this guy. 9z squared plus x squared equals 4y. 2 squareds, one's not, and they're set equal to each other. Both are positive on the right. That's going to look like this one. But instead of the z being over here, I have the y over here. So this is an elliptic paraboloid. And this guy is around the y-axis. X squared 2z squared equals 1. I'm missing a third variable. Well, the only time I'd be missing a third variable is if we have a cylinder and it kind of runs along the y-axis for this one. Negative x squared, negative y squared plus z squared. I have two negatives, one positive, and it's set equal to a positive number. That's a hyperboloid of 2 sheets. And whatever's unique, that's this one, is what you're rotating around. This would be around the z-axis. X squared equals y squared plus z squared. Everybody's positive, but somebody's on one side and the other two are on the other side. That's a cone. That's right here. Everybody's positive, but somebody's on a different side. And the x is on a different side, so my x-axis is my axis of revolution. And I've got a positive squared, a negative squared, and a non-squared. Let's see, positive squared, negative squared, and a non-squared. That is a saddle or a hyperbolic paraboloid. I'm going to call it a saddle because that's what we call it most often. And this, in a way, they're all unique because x is positive, z is negative, and y isn't squared. So what you do need to know about the saddle is that basically it's called a saddle because if you think about an actual saddle, when you sit on a horse, you'd have yourself up here. Look at this, my awesome drawing skills. There's my hands, and then my legs go this way, right? You can't see the other one, but it comes down over here. Where your body goes, that's the axis that's not squared. What you're straddling is the negative, and where your feet go is what's positive. So it's not really that anybody's, I don't know, it's not really that anything's that unique. They're all unique in their own way. So in this one, because y is that way, this would be a saddle, and I'm laying along the y-axis. That's where my body would be. So there you go. There's a whole bunch of notes on all of that wonderful nonsense. All right, really bad joke day today. I'm sorry. I can't think of many other good ones, and this one was in my son's lunch this morning. Why did Humpty Dumpty have a great fall? To make up for his spectacularly terrible summer. I know, it's terrible. I'm sorry. That's all I got. Have a wonderful day. Talk to you soon. Bye.